Hi, I'm Fabrizio and today we'll look into how to generate procedural audio in Chops. This is the first video in a series where I will try and share some of the basics on audio signal theory and how to drive sound with 3D objects, read MIDI files and translate that into visuals. Long journey ahead, hope you enjoy! Alright, if you want to generate sound before diving into Chops, it's crucial to understand a bit of a theory. First, what is sound? According to Wikipedia, in physics, sound is a vibration that typically propagates as an audible wave of pressure. So let's try and visualize it. This is a sine wave. It's a simple math function that has properties like amplitude and frequency. From the sound perspective, amplitude can be thought as volume, while frequency would represent pitch. Frequency is measured in hertz, which means number of cycles per second. So a wave that vibrates at 30 Hz has 30 full cycles contained into 1 second. Understanding frequency is also essential for work inside Chops, as it can also be used to denote resolution or the channel's sample rate. But for the moment, let's try and stick to the notion of frequency, meaning amount of vibrations. The average human can hear sounds between 20 and 20,000 Hz, but that range may vary from person to person. Higher frequency also means higher pitches, and that's why you see a long, slow wave representing a low key on the piano and tiny, squished waves representing higher keys. Now let's switch from the science into the music realm and understand how we can apply these concepts, starting with the most basic instrument, the piano. The piano tuning follows what is called an equally tempered scale, which is a discrete division of sound range into 12 steps or semitones. Each group of 12 steps is called an octave. The common piano keyboard has 7 octaves plus these 3 little keys at the lower range. Now I want you to pay attention to the A note on the 4th octave. This is a very special note. It is known as the A4 or the A440 or the Stuttgart pitch and even the standard pitch. This is the sound of the A4 note. It vibrates at exactly 440 Hz and it is commonly used as a bass note for the tuning of an entire piano. So all other notes are worked after this note. It also ensures that all pianos in the world will sound the same, independent of the manufacturer. I mean, we're not talking about the materials used in the fabrication itself, but just the sound, you get the idea. Now, you might be thinking, well, but this wave thing does not sound anything like a piano note. It's too digital, too computer-like. And you're right. Every sound we hear in real life is made of a complex mixture of many different sound waves at different frequencies and volumes, and that put together contributes to form a rich sound output. So trying to realistically reproduce a piano would involve recreating all the metal scratches that happens inside the instrument, all the wood resonation, the inner part frictions and even noises and clicks of the pianist touching the keys and pedals. That all contributes for the final sound that you hear, and that is many orders of magnitude more complex than a simple sine wave. Now you ask me, but if all sounds are so complex, how can I relate a C note played on the guitar, for example, to the same C note played on the violin? How can instruments sound the same chord? Well, although the two instrument sound waves can be very different in shape, both will share a common property, the fundamental frequency, also called the fundamental or the first partial. That concept is part of a greater study called the harmonic series. I won't go over this in the video, but basically you can think of the fundamental as being the main tone heard in any complex sound, or the one that denotes which note is playing. Every other vibration found in the sound wave apart from that is called overtone, and the result of the fundamental plus the overtones gives us the unique sound of every instrument, which we call timbre. Now let's travel one more time between words and jump from music into math. And believe me, this part is the easiest one. Okay, so let's recall the A4 note. It vibrates at 440 Hz. That's the only value you need to remember. Now let's concentrate into this 4th octave on the keyboard. We're going to calculate all other keys relative to the A. For that, we give A the index 0 and fill the indices for other keys like this. Each key represents 1/12 of the whole octave. So the simple function that gives us the note frequency is the A4 times 2 to the power of the note index divided by 12. Because remember, that is 12 semitones. So for example, let's take C sharp with index of -8. So 440 times 2 to the power of -8 divided by 12 is 277.18 Hz. And that's the wave frequency for C sharp. Now extend the indices throughout the entire keyboard and you can get any note frequency. Let's say you have calculated this C# note on the 4th octave and want to transpose that to the octave below. Just divide it by 2. You are done. The octave above, multiply by 2. You can generalize this formula by repeating the index tag we did on the previous formula, where the 4th octave receives index 0, 5th octave receives 1, 3rd receives -1, and so on and so forth. Now we can say that the transposed note frequency is the note frequency times 2 to the power of the octave index you want to transpose this note to. Alright, so these two simple formulas give you everything you need to know to recreate the entire piano keyboard in Houdini, and enough talking, let's do some practical example. Alright, in an empty scene, let's create a chop network. In the IV side, I'm also going to create this wave node. And let's go to the motion effects view and click this display flag here. Okay, so now we can see our simple sine wave, and here we have the main controls are period or frequency and also this amplitude, right? So as you saw in the theory part, it's a good idea to work in hertz, which means cycles per second, but in this case here the period is actually the inverse of that, so it's seconds per cycle. Alright, so we have it takes exactly 1 second to do one entire oscillation. I say seconds only because on this common tab here my time unit is set to seconds, but it could be also frames or samples. Okay, so it's one second per oscillation, but let's visualize that better. Let's set our timeline from 0 to 24, and as I'm working at 24 frames per second, we have exactly 1 second of channel here. And as you can see, although it has only 1 second, my timeline still, my motion effects still displays the whole 240 frames. And that's because Chops has a very aggressive caching system, alright? So if you want to update that manually, you will find yourself constantly needing to go back to this common tab and click this unload box here. Okay, and now it updates, and let's get back to the waveform. And I'm also going to click this frame indicator so that you can see where are our timeline. And now you can see that it takes 1 second to do a full oscillation. If you want 2 oscillations, we can set this period to half a frame or half a second, and you have 2. And if you want, for example, 5, you can divide and do all the stuff. But it's easier to work in hertz, right? So to work in hertz, we can just do 1 divided by the number of hertz. For example, 5. I put 5 here, and now it has 5 oscillations into 1 second. And now you can see this this little curve here. It starts to get very coarse, and you can press D on the keyboard just to see the dots or the divisions. And now we need to up the resolution, and for that we need to go to this channel tab and change the sample rate. So you can think of this sample rate as being the resolution of a channel, right? So you can up here and you see more dots and the rounder shapes. Now a little bit of background here. For audio, we need lots of samples, and that's because we need lots of smaller frequencies here, so that we can hear something. Okay, we have very large or very spaced waves, so we are not going to hear anything. Just as a reference, for CD audio quality, is common to have 44.1 kilohertz of frequency data, which is 44,100 hertz, so it's a lot. So let's up that to, let's say, 10 kilohertz or 10,000 samples per second. And now let's go back to this waveform and let's try and vibrate this thing at the mid octave A note on the piano, so 440 hertz. So let's try that. Okay, and that's what it looks. And as you can see, now we have a lot of information here. You can really zoom in and to see the dots. Okay, so let's hear what it sounds. To send that to the playback, we can just open this Windows audio panel here, or Alt I. Let's change that to this scrub tab here, and also I'm going to set that to mono, and let's just drag and drop this node here to this chop. Also be sure to have this real-time toggle check it, because let's give Houdini enough time to calculate all this thing before sending to the audio device. I'm also going to set this timeline to a little bit more than 24 frames, so let's say 240. And as always, you need to go to this wave node and click this unload so that updates. So you can see the whole, and here you can see how much information we need for audio, right? So you can see a solid thing here, and you can really zoom in to see all the divisions. So lots of information, and that's the reason why Houdini can handle like real-time audio. It constantly needs to be like recorded or something like that to if you want to do like pitch modifications or equalizing or stuff like that. Okay, so yeah, let's hear that. So Alt Y to bring up the panel again. Let's play that. And this is the A4 playing. Okay, cool. So that is the basics of playing sound in Houdini, and let's move on to some more advanced topics. Alright, so now let's take a look at the oscillator. So this node does kind of a similar job to the wave node, but does with more control. So right from the start you can see it has 3 inputs, and the first one is the pitch control, which means you can use another channel and to vary the frequency we're going to play here in this node, right? So now we can start to see some similar values here. So for example, we have this base frequency set to 440 by default, which is 440 hertz. So yeah, that's actually the A4 node, and that's why it's the default here. So it's a very common value. And also we have this octave thing here, so we can divide or pitch, or we can pitch control or input channel here is going to be in fractions of an octave. Okay, so right now it's set to 1, which means if we input a constant channel with value 0, it's going to play this base frequency here. If we put that to 1, it's going to send that 1 octave above. So if we're playing the A on the fourth octave with input channel 0, if we send a new signal of value 1, it's going to play at 880, which is the A on the 5th octave. Okay, so yeah, so what we want to do here, if we want to play at the semitones level, we need to put units per octave of 12, right? 12 semitones into an octave. So let's start and check these sounds. So let's input a constant channel, so a constant node that generates one channel, and I'm going to call that sound, and it has value 0. We also need to set the instead of single frame, let's play that for I don't know, 2 seconds, because remember we have this time unit set to seconds. Our sample rate will be 10 kilohertz, and let's send that information to the pitch control here. All right, and also let's visualize that. I'm clicking this node just so that it updates and unchecks this one, because if you click, you can display that both channels. If you want to display only one, you can control click, and now it displays on that channel. All right, so now let's visualize that better. And again, has low sample rate, and that's because the oscillator itself has this channel sample rate, and let's up that to 10 kilohertz. All right, and now let's check what it is playing. But before that, let's open the audio panel, set to scrub, and in this chop file, I think instead of switching every time, it's a good idea to just create a node here, and let's call that play. And I'm going to give that a nice green color, and then send that to the playback. Okay, so let's visualize that, and this is what I hear. So let's play. Great, so this is actually playing again the A note, the A4, which is 440 hertz, and that's only because our input channel is set to 0, which is the base frequency itself. So let's try and up that here in this constant channel. So let's play that. Oh, actually, let me put that to 2 seconds again. Let's play that. So still A. Now let's change to 1. So this is A sharp, B, C sharp, and so on and so forth. Okay. So that's how you can control on a semitone basis. So you are playing the notes following by these indices. Wonderful. So let's move on a step further and start bringing in dynamic data into this chop network. And let's move on to scene view again. And also let me create a simple geometry container that's going to be a box. And we are going to now drive that pitch control with the translation of this box in X. So let's do that, and let me give it some animation just to start. So I'm going to set my timeline to 100 and let's give it some animation. So let's key at frame 0, at frame 24, and excuse my sound, let me not play that while we animate. So frame 24, that's going to be 1, and then at frame 48 we go back to 0. Okay, very simple animation. So let's see how we can bring that back to our chop network. So inside our chop network, I'm going to delete this node. We don't need that anymore. So let's create a import fetch parameter node, and we are going to import information from this geo1 node, and the channel is tx, or translation in x. And let's see how we can use that value. Well, it's very simple. We just need to plug that into the pitch control. And let's visualize. Again, I'm going to split my view into 2, and let's change that one to the motion effects view. Great. So let's use the full animation range, and yeah, let's see what it sounds. I'm going to down my volume a bit because I think it's too loud. And now also I'm going to change the animation to be a little bit further. Instead of 1 semitones, I'm going to move by, let's say, 5 semitones. Okay, so let's see what is the result. Yeah, so we can start to bring in some and start linking 3D content to our audio generation. But now we are just like importing sounds in between semitones, which sounds like a little bit of not too musical, because we usually hear like the notes separately. Now we are just hearing them like interpolating. So to stay more true to a musical stuff, let's try and, for example, create the Happy Birthday to You song just using the position of this cube. So for every unit it goes to the side. It's like we are playing a different key. Okay, so let's I'm going to quickly create this animation, and we'll see how it sounds. And here's our Happy Birthday song. Yeah, I know, that's a bit lame, but okay, you get the idea. But now it lacks a little bit of rhythm, right? It's just playing notes, and it doesn't know when to start and when to stop. So we need some way to also create a trigger for the notes, right? So when it plays and when it should stop. So let's do that. Alright, so to create a trigger or an on-off state to our notes, I'm going to drive that with the Y position of the box. And we are going to send the information, and let's say for the 0 position here, the note is going to play, and for the 1 position like this, it's going to be off. Okay, so it's like the cube is touching a keyboard, right? So let's do that. I'm going to uncheck this animation, and let's set to 0. And the way we can do that is by going to our chop network, and we are going to fetch one more channel. So again, we could fetch the two information right from here, but the problem is that this oscillator node creates one wave for each of the channels. So I prefer to do that separately. So I'm going to fetch again, but just the transformation in the y-axis. And the way we're going to do that is by first we need to switch values, because the 0 position here is the note on, or the value should be 1, and the 1 position in y should be 0, or the note not playing. So you need to inverse this data. All right, so to do that we can drop a math node, and we can just go to this range and do a remap from 0 to 1. It goes 1 0, and we are inversing the value. And now we can just multiply the result of this channel by this one, and it's like we are multiplying the amplitude or the volume of this channel by this value here. Okay, so we need another math node, and we just input this one and this one, and the operation here is the combine chops. We need to do multiply. So this is going to make our channel be multiplied by that value. So let's visualize that in the motion effects view, and let's try and animate this. So for the first frame the value is 0, but let's say on the frame 24 this value is 1. Alright, so watch what happens. So the volume of the sound is diminishing according to this y position. So let's say we want to do, for example, this note is off, but then again on the frame 48 the note is on again. So it's like we're touching the keyboard. And let's play for a little while, and let's create another key, and let's up our virtual finger again, and that's how we can create this on-off switches. So let's play and see what it gives us. So you see we can create our sound trigger here. So I'm going to again quickly animate that through the sound so we can see what the results are. And here's the result. I've also tinted the box red when it touches a key. So let's see what it sounds. Cool. So yeah, it lacks rhythm, but it's you see, you can do a lot of things with this. And this is a very basic idea for working with sounds. We can expand this a lot. In the next videos I'm going to show you how we can do something like a piano keyboard that reads MIDI files, or a simple audio that is generated through physics, and when objects touches another's, and we for example cloud simulations, how can it vibrate to produce sound and stuff like that. Okay, so it's a very cool area to experiment, lots of stuff to do here. Yeah, so that's a very basic understanding of how to input audio in Chops, and I hope you like it. And as always, if you like this video and if it benefits you, please consider supporting my Patreon page. I've also uploading all these scene files for my patrons, so if you want to download and play with that, you can just go to patreon.com/fshamo and you get all the files. Okay, so yeah, hope you like it. Until the next video, bye bye.